Okay, we're going to go through the structure and properties of materials. In general, we're going to look at structures and properties of actually all the different types of bonding. Okay, so the different materials, they can either be ionic bonding, covalent bonding, or metallic bonding. They will have different structures and different properties as well. So depending on what type of bonding it is, it will give different type of properties. So let's go through this now. Okay, do take note, this will be 2 pages. First page will be comparing the different types of bonding: ionic, covalent, and metallic. And for covalent bonding, we'll just be focusing on the simple covalent molecules. In the second page, we'll be focusing on covalent bonding, but the giant covalent structures. So all of these silicon dioxide, diamond, and graphites, they are under the giant covalent structures. Okay, so just to highlight again, once again, first page will be on ionic bonding, covalent bonding, but for simple covalent molecules, and then we'll be doing metallic bonding. Okay, that's the first page, and second page will be dwelling into the giant covalent structures. Okay, so let's start. So first up, ionic bonding. So substance, when they undergo ionic bonding, they will actually form what we call a giant ionic crystal lattice structure. How it looks, it'll look like this. Okay, so each of these different circles represents different ions. So if the green circle is a positive, this purple one will be a negative, and it will just alternate to form this giant ionic crystal lattice structure. Now take note, all 4 words needs to be there when you're describing the structure for ionic bonding. This is formed between metals and non-metals. The metals will be forming the cations, okay, and the non-metals will be forming the anions. Okay, so this is for your ionic bonding in terms of structures and the combination of elements. Now, for covalent bonding, the most common one that you tend to see is the simple covalent molecules. So they exist as simple molecules. Like the word covalent just there to highlight what type of bonding it has. Okay, so they exist as simple molecules. So simple molecules are actually your countable molecules. So you can actually see here, I got 5 different atoms combined, okay, to form this molecule. Okay, this one here I have 4 that's combined to form the molecule. So all of these are simple covalent molecules. So they are countable. They are molecules with countable number of atoms. Okay, with countable number of atoms. Okay. Now, so for covalent substances, the combination of elements, they are actually formed by non-metals only. Last one, metallic bonding. So for just want to go back here. The non-metals, take note, they will actually share electrons in their valence shell. So this is just to highlight the kind of bonding. And this, in terms of this particular thing here, okay, when they share, they form this bond. This is your covalent bond, and this is actually strong. Okay, strong covalent bond. Now for metallic bonding, now let's go on. Okay, how would you describe the structure? It's a giant metallic lattice structure. Now, what does this giant metallic lattice structure consist of? It consists of a lattice of positive ions. So lattice is generally this kind of regular arrangement. Okay, so all of these cations are actually present, and take note, they are in fixed position. Okay, because typically they are solids, and they are surrounded by a sea of delocalized electrons. So this description, put a star here, take note whenever you are describing the structure for metallic bonding, is this whole chunk of text that needs to go in. It's not just a giant metallic lattice, but what is this lattice consisting of? Positive cations in fixed position in a sea of delocalized electrons. How does metallic bonding work? This is where the metals, they lose their electrons. Okay, when they lose their electrons, they become cations. So that's where they form the lattice. And because they lose their electrons, this electron actually forms the sea of delocalized electrons. Okay, now, so in general, these are the structures of how you describe it. These are the structures for the ionic, covalent, and metallic. Okay, and then in terms of the combination of their elements. In general, also as well, the state at room temperature and pressure, RTP stands for room temperature and pressure. Okay, so usually at room temperature and pressure, ionic compounds tend to be solid. Covalent substances tend to be gas or volatile liquids. Volatile means evaporate very easily. Okay, and the last one, metallic bonding, metals tend to be solid. Okay, so now we are done in terms of the general describing the structures and then what kind of state it exists in at RTP. Now let's look at the properties. So there are three main properties that we're looking at. One is the melting boiling point. Two is electrical conductivity. Three is the solubility. For melting and boiling point, you will need to explain it. For electrical conductivity, you will need to explain it. For solubility, there's no need to explain it, just need to know the property itself. Okay, so we're gonna go through them one property at a time. So let's start with ionic bonding. So ionic bonding, their melting and boiling point is high. So typically their melting boiling point is high, means that they require a lot of, what does it mean? It means that a lot of energy, okay, this is the first point in your stick note, a lot of energy is required. Because high melting boiling point means you must absorb a lot of energy. What is this energy used for? Okay, it's used to overcome, so second word to take note, overcome what thing? Strong electrostatic force of attraction. Now, this electrostatic force of attraction is strong, so I just want to take note the word strong here. Not just only strong, but you must describe what is the electrostatic force of attraction formed between. So it's between oppositely charged ions. Okay, so people tend to miss out terms, okay, over here whenever they are trying to explain why high or low melting boiling point. So these are the 4 points that you will need. Now, let me use a different color at this point. So, just want you to take note, ions with higher charges will tend to have stronger electrostatic force of attraction, which result in higher melting and boiling point. Think about it, plus and minus, strong attraction. Now what if the charge, the positive charge is 2 plus and the negative charge is 2 minus? You realize that by having higher charges, this attraction between them will actually be stronger. Okay, so that's what this note here is telling you about. So that's for ionic bonding. They have high melting boiling point. Then the question now comes with, okay, so if ionic bonding has high melting boiling point, how about covalent substances? So covalent substances, okay, they have low melting boiling point. So question is, isn't covalent bonding, you tell me, strong? How come it has low melting boiling point? Doesn't it require a lot of energy to break the strong covalent bond? So take note here, little energy is taken in or required. That's the first point you need to say. Second thing, the word overcome. Now what are they trying to overcome over here? It is the weak intermolecular force of attraction. Now take note here, we are looking at weak intermolecular force of attraction. This is not the strong covalent bond, not the strong electrostatic force of attraction between the electrons and the nucleus. No. What is this weak intermolecular force of attraction? So for example, okay, let's use hydrogen as an example. So hydrogen bonded to another hydrogen, right? So this is my strong covalent bond. Now, when I'm trying to melt or boil hydrogen, okay, I'm not trying to break the strong covalent bond. So what I'm trying to do is, between molecule 1 and molecule 2, there is these two molecules. Between these two molecules, there's this blue color force of attraction. This is my weak intermolecular force of attraction. Okay, the word intermolecular tells you that it's between molecules. So intermolecular tells you it's between molecules, and it is actually a very weak force of attraction. Okay, that's why in terms of covalent, simple covalent molecules, it has low melting boiling point because you're not breaking the strong covalent bond. Actually, you're breaking the weak intermolecular force of attraction. That's why little energy is required to overcome the weak intermolecular force of attraction. Now, this is one thing to note, okay? Simple molecules, if you got higher relative molecular mass, they will have stronger intermolecular force of attraction. Here I shouldn't use red, I should just use blue, similar to jet. So take note, if you got higher MR, they have stronger intermolecular force of attraction. Okay, so if I just compare BR2, sorry, let's not use BR2. Let's just compare very simple one. Cl2, the MR is 71 versus I got O2, the MR is 32. Which one will have a higher melting boiling point? Answer is this guy here will have higher melting point, boiling point, because higher MR. Okay? Now, second point I want to take note is when you're melting or boiling the simple covalent substances, the weak intermolecular force of attraction is overcome. There's no change to the strong covalent bond. The covalent bonds remain strong and you are not actually weakening it or any other single thing. Okay? So take note. Now, what I'm highlighting in red at the top over here, okay, and over here, this is the explanation. You don't need to write the note. All this note over here, don't need to write down. We are trying to explain whether low or high melting boiling point. Last one, in terms of metals, metallic bonding. So they have high melting boiling point. How come? So look at the language again. Once again, a lot of energy is required. Okay, to do what? Overcome what thing? The strong electrostatic force of attraction. Now, once you're talking about strong electrostatic force of attraction, you must tell me between what? So between the lattice of positive ions and the sea of delocalized electrons. Okay, so you can see here the description. Okay, between the three of them, it's always about energy. It's always about overcoming. Then the last part is always overcoming about what type of force of attraction. So you're able to identify it correctly, write the correct terms, you're safe, you're good to go. Okay, now, so in terms of the note-wise, okay, for metallic bonding, note, metals with cation ions of higher charges will have stronger electrostatic force of attraction. Due to cation ions with higher charge, also have more delocalized electrons. So think about it, if my cation ion is 3+, you realize, hey, the charge is higher. Yes, so if the charge of the cation ion is higher, to get 3+ means that actually I would have each atom, I would have released 3 electrons. 3 electrons, 3 electrons, 3 electrons, 3 electrons, 3 electrons, 3 electrons. So realize that there will be 3 times more electrons. The cation ion charge is also 3 times. So this will actually result in a stronger electrostatic force of attraction. So just take note of that. Okay. So in terms of the melting boiling point, we have explained between ionic, covalent, and metallic. Now we're going to go on to electrical conductivity. So when we look at electrical conductivity, we are looking at whether is there mobile charge carriers. Now, for a substance to conduct electricity, charges must be able to move inside there. There must be some charges inside there that can move, and hence it will be able to conduct electricity. If there are no charges that can move, then it cannot conduct electricity lah. Okay? So for ionic compound, they can conduct electricity only in molten, which is very hot liquid state, or aqueous state. Okay? So conduct electricity in molten or aqueous, but not in solid state. So liquid or molten state and aqueous state, they can, but solid cannot. So reason, why is it so? So take note, in molten and aqueous state, okay, that will be the first thing. You want to tell me what state they're in. The ions are mobile, because the ions are like the particles, right? When they're in liquid state, the particles are sliding over one another, so they are mobile. If they are mobile, means they can move. They are able to act as the mobile charge carriers. Means that they are charges that can move, and hence they can conduct electricity. So how come in solid state they cannot? So for this bottom part here, so in solid state, ions are only able to vibrate in their fixed position. This word fixed position is important. Okay, so they only vibrate in fixed position. So realize, hey, this is kinetic particle theory. This is about the solid particles are held in fixed position, vibrating in a fixed position. So if they are vibrating in fixed position, what's the impact here? What's the results of it? They are not mobile. If they are not mobile, they cannot act as mobile charge carriers. So all this 1, 2, 3, 4, it tells you that these are the phrases, the points that you need to write down to fully explain why it is not able to conduct in solid state. So for ionic substances, they can conduct electricity in molten and aqueous state, but not in the solid state. Okay? Now, how about simple covalent molecules? So they cannot conduct electricity, so does not conduct at all in any single state. So why? It's because they are neutral molecules. So they are neutral. So if they are neutral molecules, they do not have any mobile charge carriers to conduct electricity. Okay, they do not have any mobile charge carriers to conduct electricity. So very simple explanation, neutral molecules do not have any mobile charge carriers to conduct electricity. Now, how about metals in metallic bonding? So they can conduct electricity in solid and molten state. Solid and molten state. So why is it so? It's because they have the presence of the C of delocalized electrons. The presence of the C of delocalized electron, they can act as mobile charge carriers. And hence, they are able to conduct electricity. Okay? So realize, key idea here is always, what is the mobile charge carrier? In terms, if once they have a mobile charge carrier, you can say that they can conduct. If they don't have, then they can't conduct electricity. Okay? The last property would be in terms of solubility. So ionic compounds, this one just know lah, they are soluble in water, but insoluble in organic solvent. Okay, soluble in water, but insoluble in organic solvent. For covalent substances, they are insoluble in water, but then they are soluble in organic solvent. Then the last one, for metals, they are insoluble in both water and organic solvent. Okay, so both also insoluble. So just take note of these two things, okay? So just take note of these two. Okay, so this is in terms of all three of them. My general ionic, covalent, and metallic bonding. So this applies to generally most of the ionic, covalent, and metallic bonded substances. Okay, so this is the first part here. Now let's go on to giant covalent substances. Okay, for giant covalent substances, we shall now look in the general one first. So this is the first thing I will go through. After that, I'll compare these two. Okay, then I'll go on to doing graphite. Okay, in general, this is the flow that I'll be doing lah, but I may just switch between here and there depending on how it is. Okay, so in terms of covalent bonding, we got simple covalent molecules as one of the structure. There's a second structure that it can have, which is called the giant covalent structure. So they exist as a giant molecule. Okay, so giant covalent. So they're actually one big molecule if you think about it for your giant covalent substances. So because it's covalent bonding, they consist of the non-metals only, that they share their valence electrons. Okay, now the particles present obviously in covalent substances is atoms. They generally at room temperature and pressure will exist as solid. So a little bit different, actually quite different from your simple covalent substances. So why is giant covalent substances different from your simple covalent molecules? So let's compare the three properties first. So in general, giant covalent substances, their melting and boiling point is high. Why high? So same thing, let's look at the reasons. So a lot of energy is required, so that's the first thing. So a lot of energy, that's why high melting boiling point, right? But why? What is this a lot of energy that's required to do? Is to take note, is a lot of energy is required to break. So what I'm doing here, I'm not overcoming force of attraction, I'm breaking. What am I breaking over here? I'm breaking the large number of strong covalent bonds. Where are they found? Between the atoms in the giant structure. Okay, we'll go in depth into what the various covalent bonds are are referring to. So in terms, just take note of this in terms of the general description first. Once we go into the specific substances, I'll explain more to you what the large number of strong covalent bonds are. In terms of electrical conductivity, they do not conduct do not conduct electricity in any state, because why? They just have no mobile charge carriers, so absence of mobile charge carriers. These few parts here, there's really hardness, don't need to worry too much. Reason also don't need. Solubility, they are insoluble in all substances, all solvents, okay? Whether organic or water, also cannot dissolve. Okay, so that's the general giant covalent structure. Now let's go into specific, in terms of giant covalent structure, now let's look at silicon dioxide and diamond. So for silicon dioxide, what is this giant covalent structure that we are describing? So first up, let's go into it. This is the structure of my silicon dioxide. So let's look at this description here. So each silicon atom, okay, each are, what do? They form strong covalent bond. So each silicon, so let me use a blue highlighter. So each silicon, oops, maybe I should, actually cannot, let me use this blue. Each silicon atom, this blue color one, okay, blue color one, okay, it is bonded to 4 oxygen atom. So where is my oxygen atom? Let me use a different color to show you. Let's use green. So this is the oxygen atom. Oxygen atom, oxygen atom, oxygen. You realize that each blue color is bonded to 4 oxygen atom. Okay? That is the silicon atoms bonding. And each oxygen atom forms strong covalent bond once again to 2 silicon atoms. So each silicon bond to 4 oxygen atom, but each oxygen atom, if you look at it carefully, only bonds to 2. Okay, so you realize for each of the green color, it only bonds to 2 other silicon atom. Okay, so you need to describe when you talk about this giant covalent structure, you describe how the bonding works. Each of the atoms bond to how many of the other things around them, and this thing actually extends throughout the structure. Okay, this bonding actually extends like infinitely. It gives a 3-dimensional network structure, okay, in a tetrahedral arrangement. So tetrahedral means it's like a four-sided kind of shape. So in general, each of them will actually bond with 4 other things kind of idea. Okay, so you can see, let me use a different color over here. Let's use yellow. Yellow is a bad color, red. Okay, so there's 1 phase over here, 2 phase. The 3rd phase is behind. The 4th phase is... Okay, sorry, let me erase this thing. Sorry, let me explain again. Okay, so 1st phase, 2nd phase, the 3rd phase is behind, and the 4th phase is at the bottom. So each of them will form this tetrahedral arrangement. So when we describe this giant covalent structure, this is the idea over here. Okay, this is the giant covalent structure that we described. So for silicon dioxide, this is the description of structure. Obviously, it's between what the particles present, silicon and oxygen atom only, because it's silicon dioxide. This one can sometimes think of your sand, or sometimes they describe this as also quartz as well. Okay. Now, so in terms of melting boiling point, because they are giant covalent structure, obviously their melting boiling point is high. So why is it high? So you will look at the description for giant covalent structure and look at specifically for silicon dioxide. So why high melting boiling point? Once again, a lot of energy is required to break what? The large number of strong covalent bonds. In the general one, we say it's between atoms in the giant structure. In this case here, for silicon dioxide, we know what are the atoms. So we need to be very specific here. It's between the silicon and oxygen atoms in the giant structure. Okay? So you're actually breaking the whole network. So imagine for this one here, every single bond, you're breaking it. You're trying to break every single bond whenever you're trying to melt or boil it. And hence, it is a whole ton of energy required to break the whole structure. So it's different from a simple covalent structure, because simple covalent structure at the top, we are referring to weak intermolecular force attraction. This blue color line dot over here, right? These are weak. But when we look at giant covalent structure, we are trying to break all these strong covalent bonds, and it's a whole network of them, and that's why there's a lot of energy required. Okay? Now, in terms of electrical conductivity, they don't conduct electricity in any state. Very simple idea, because really there's just no mobile charge carriers, absence. There's no mobile charge carriers. Okay, don't need to describe hardness, don't describe reasons for the hardness. Solubility wise, insoluble in all solvents. Okay, water and organic solvents as well. Okay, now let's go on to diamond. Okay, for diamond here, I want you to look at the structure for silicon dioxide and diamond. Do you realize they are almost identical? So, do you realize that this one also has this tetrahedral arrangement? One face, two face, then third face at the back, and then the last one at the bottom. Okay? So, diamond and silicon dioxide are actually generally very similar. Okay? But in terms of the structure description, it's slightly different. So, diamond is a giant covalent structure, covalent bonding. How to describe the structure? Okay, so let's zoom in here. Let me erase this. So, let's use blue color to show. Okay, so they say each carbon atom forms strong covalent bonds to 4 other carbon atoms. So as you can see here, each carbon atom forms strong covalent bond to 4 other atoms. Okay, and this carries on, right? This whole thing here, you can see the whole network spreads out. So this gives a 3-dimensional network structure in a tetrahedral arrangement. So the whole so when they use the word network structure, it tells you that it's just 3D and it just spreads throughout. Okay, it's like an extensive structure. So this is how you describe your diamond giant covalent structure, and this is the visualization of it. What kind of atoms does it have? It only have carbon atom now. So diamond is actually made out of carbon atoms only. Okay, so once again, we're going to look at, in terms of the melting boiling point, it is high. And because there's high melting boiling point, generally exists as solid in room temperature and pressure. Same for silicon dioxide, right? Okay, but let's go and zoom in to describe why is it that it has high melting boiling point. So a lot of energy is required, once again, because high melting boiling point. To do what? In this case, is to break. So once again, for giant covalent structure, we are breaking the bonds. We are not overcoming it, we are breaking. So a lot of energy is required to break what? The large number of strong covalent bonds. Okay, take note, the word large is important. This large number of covalent bonds is between what? Between carbon atoms in the strong giant structure. Okay, don't just stop at between carbon atoms. Why is there a lot? Is because there's this whole giant structure with the tons of bonds that I need to break. Okay. Next, conducting electricity, absence of mobile charge carriers. Okay, that's why they does not conduct electricity in any state. Now, this is the part where they talk about hardness. Why are diamonds so hard? It's actually one of the hardest material in the world. Okay, so you know that in terms of degree of hardness, diamond is hard. Why is diamond hard? So first thing you realize, diamond, each carbon, okay, forms strong covalent bond, okay, to 4 other carbon atoms. Okay, so this is a network of structure. This is a whole 3D structure, right? 3D network structure. So what happens is that because of this whole structure, a lot of energy is required to break the let me underline. Okay, to break the strong covalent bonds. Oops, I realized there's a repeat. Okay, strong covalent bonds in the giant covalent structure. Well, you realize, hey, this one quite similar to the melting boiling point. Yeah, similar. Okay, it's just that in this case here, I'm not supplying heat energy. In this case, I'm supplying like a force, and this force here is the one that's supplying the energy to break the bonds. Okay, that's why I talk about hardness. Okay, so very similar in terms of diamond. Now, in terms of the melting boiling point and degree of hardness. How about the next one? Okay, so why is it that you are studying silicon dioxide, diamond, then graphite? So if I go from the general idea is that silicon dioxide giant covalent structure, then the pattern is a tetrahedral shape, right? The whole 3D network structure of tetrahedral shape. Then I go into diamond, right, using carbon. Then I go on to talk about graphite. Why graphite? Is because you realize graphite is also made out of carbon atoms only. So diamond and graphite, actually there's a term given to both of them. They are known as allotropes. What exactly are allotropes? They are elements, okay, with different structure. So you see, both of them are carbon, but they behave differently because of the different structure. Now, so let's look at what's the difference in structure. So for graphite here, once again, giant covalent structure. Say, same giant covalent. But look at the description here. Each carbon atom forms strong covalent bond. Okay, so far same. Now take note. For diamond, it is 4 other carbon atoms. For graphite, it is to 3 other carbon atoms. Okay, to 3 other carbon atoms. And this actually, look at the description here, it gives a layered structure. So it's layered, consisting of what? Hexagonal rings of carbon atom. So if you look at the diagram here, do you realize this is a carbon, 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 carbon? It forms a hexagonal ring. Okay, forms a hexagonal ring. So that's what they are highlighting here, hexagonal ring, right? And the ring extends. Okay, so you can see the hexagonal ring. And now, take note, they are in layers. So this is one layer of graphite. This is another layer. Okay? So this one is by layered structure. Layered structure. Okay? So now, in terms of melting boiling point, so once again, it is high. You look at the description here. So a lot of energy is required to break large number of strong covalent bonds. Between what? Between carbon atoms in the giant structure. Very similar description to diamond. Very, very similar. Okay? In terms of electrical conductivity, this is where it gets interesting. So this is the first giant covalent structure that you realize, it can conduct electricity leh. But take note, you need to highlight that it is along the layers. Okay, so when I say along the layers, means along the layers like that. It cannot conduct, so let's use blue. It cannot conduct across layers. Only along the layers, but not across the layers. So why is it so? So take note of the explanation. So we know that each carbon atom is bonded to 3 other carbon atoms. This is an important statement to write. So because each carbon atom is bonded to 3 other carbon atoms, this leaves 1 unbonded electron per carbon atom. Now a lot of people just say 1 unbonded electron. Now this unbonded electron per carbon atom. So if I've got 20 carbon atoms, it means that I've got 20 unbonded electrons. Okay? Now if this electron is unbonded, take note, they are free and mobile, or you can say free and delocalized. And because they are free and mobile, or free and delocalized, they can finally act as mobile charge carriers. Once you can act as mobile charge carriers, they can conduct electricity already. Okay, so for graphite, they are able to conduct electricity along the layers because of this particular thing here. Okay, now take note, these mobile charge carriers can only move along the layers, but cannot move across layers. Okay, they can only move along layers but cannot move across layers. So just take note of this. Okay, last one. So in terms of hardness, okay, so we know that graphite and diamond, they are allotropes. They are like carbon, but they have different structure, right? Based on what we can see here, different structure. Okay, different structure. And this difference in structure actually results in electrical conductivity difference. Okay, difference. Next one, in terms of degree of hardness, there's also difference as well. So diamond is hard, but graphite is soft and slippery. That's why actually your pencil lead is made out of graphite. It's able to you're able to write on it because it is soft and slippery. So why is it so? So take note, in graphite, there are weak intermolecular force of attraction. Where is this weak intermolecular force of attraction? Between layers of carbon atoms. So we go back to our diagram here. Where is it? So let me erase. Let me use maybe green color. So one layer, this first layer, this second layer. Between these layers over here, this is my weak intermolecular force of attraction. Okay. So because these are weak intermolecular force of attraction, what does it mean? It means that I will require little energy, okay, which requires little energy to overcome. Take note, this is not break to overcome. When we talk about weak intermolecular force of energy, we talk about overcoming it. And because it requires little energy to overcome, the layers can slide over each other easily. Okay, this is the fifth point over here. So look at the way how it is being phrased over here. Okay, so we actually went through the three different types of bonding in terms of ionic, covalent, and metallic. But for covalent bonding, we went through simple covalent in the first page. In the second page, we went through the giant covalent structures in specific. Okay, the silicon dioxide, diamond, and graphite. Okay, and then we highlighted diamond and graphite. They are considered allotropes. Okay, so this is the end for this whole structure and properties of materials. Do take note, phrasing is key here. I purposely underline and write the 1, 2, 3, 4. It's really tell you what are the points you need to take note of when you're writing the thing. So there's quite a bit of things to memorize in this chapter. Just remember that we are quite particular over terms for this particular chapter. Be familiar. The more familiar, the more you practice on this, you realize the standard statements, you'll be able to write them better. And try to spot pattern between the different style of writing as well. Okay, so that's all for this. Okay.